James McInerney from, I hope I'm saying your name right, that from Netflix. He's also been at Spotify, has got a great background in both Bayesian computation and Bayesian inference and in recommender systems. And I'm looking forward to hearing his presentation about Thompson sampling for scalable Thompson sampling for non-conjugate models. So are you able to share, James?
Yeah, working on it now.
You should be able to.
Oh, I see. Okay.
Okay.
Can
you see something? Yes, that looks right.
Okay. Does it look good? Okay.
Yeah. Okay.
Yeah, so thanks, David. Thanks very much for putting this workshop together. Thanks for having me. So I'm here to share some new research on how to do exploration with more of the kind of modern approaches that are definitely non-conjugate and maybe even more difficult to explore using the standard methods. So I'll dive right in. So the problem of exploration and recommendation comes up a lot. So if you think of recommendations as a collaborative filtering problem, where the rows are the items that are being recommended and the columns are the contexts. The context can be anything you want, really, that will kind of inform you about users. We're often faced with this outer matrix prediction problem. So if I'm a new user who comes from London and you've only seen users in California and New York, there's a problem of extrapolation for the existing items. There's also the cold start problem, which is recommended system grows the number of items, and how do you extrapolate to new items in the system? So this is definitely a very challenging exploration problem. And Thompson sampling is, as John Langford was mentioning earlier, it's a workhorse method for approaching exploration. So the idea is, given a data set, a likelihood and a prior, so that's a model, iterate over the following two steps. So first of all, sample the model variables from the posterior distribution. And second of all, pretend that sample is just the truth and feed it through to give you a predicted reward, and then pick the action that maximizes the predicted reward for that sample. And as you get more and more data, your posterior will concentrate, and you'll have less variation for the samples, and that would be more of an exploitative policy. So you get this natural exploration to exploitation phenomenon. And the problem is, unless the posterior, unless the that's a type, well, that's not a typo, unless the likelihood and the prior take the same form, so they're conjugate, unless that's the case, the posterior calculation is prohibitive for many models, right? So even if we can write down the joint likelihood and take Monte Carlo samples, we've discussed earlier that the challenges around that for scalability and for being able to get it implemented practically when there's a laundry list of other tasks that need to be done in a recommender. And so this happens a lot with neural networks or GBDTs or random forests. They present challenges for quantifying uncertainty, and it's hard to apply the existing exploration schemes like UCB and Thompson sampling. And I see two dimensions to the zoo of methods out there. So the first dimension would be, I guess, the x-axis, which would be how much uncertainty are we capturing, and what type of uncertainty are we capturing. So on the left-hand side, I put something like epsilon greedy or Boltzmann exploration or last layer variance. So those give some notion of exploration, some more nuanced than others, but they don't capture what you call the epistemic uncertainty around the parameters of your model. So it's a shallow form of uncertainty. And if you go to the right-hand side, the right column, these will be the methods that capture model uncertainty. And these can be split between methods that are computationally expensive and computationally inexpensive relative to the base model. So, right, so if your base model is a huge neural network, you know, you could say that that's expensive in itself, but I'm talking relative to that. So on the bottom right, you have model-specific approximations, like the Laplace and residual overfit, which is this talk. And then the top right, methods like bootstrapping and MCMC. So yeah, I really want to focus on the bottom right quadrant of this, because I think that's the most compelling when it comes to real-world interactive systems. So it's sort of a riddle that I've been asking myself, that I'm intensely curious about, is we developed all these methods for avoiding overfitting or fighting overfitting. Very elegant, incredible methods like a Bayesian model, averaging, you know, model selection, dropout, regularization, you know, the list goes on and on. And this is all against reducing overfitting or mitigating it. But I've been curious about whether overfitting can ever actually be useful. That's the question. So let me define something that I call the residual overfit. So in the residual overfit, there are two models that are being fit. The first is a regularized model that I call F. So that's our best attempt at capturing the true reward function. So we use every trick in the book we can to make that an accurate model to minimize you know, out of sample error or test error. And then there's another function we'll call G, which would be unregularized, and you know, we don't care if it overfits. In fact, we want to encourage it to overfit the training data. So if H is the unknown true function, then let's just assume that F is some perturbation on H, and G is another perturbation of H, and F and G have independent errors, and you know, as a result of overfitting, you'd expect the expected epsilon to be 0, so there's no bias there. And the concept of residual overfit is just the absolute difference between the predictions of these two models. So the claim would be that the squared residual overfit is an upper bound on the error of F with respect to the true function H. So here's a kind of napkin derivation. So if we take an expectation of the squared residual overfit, we can expand it out by the definitions. We see that the H's cancel, and we're left with the errors of the two models. And because they're independent, we can split them up. And so it's the case that the expected squared residual overfit is an upper bound on the mean squared error of F, because variance of G can never be less than 0. And just a reminder, this holds in expectation and also requires the independence, which we can always achieve by data splitting in some way. Another perspective on this is a little more nuanced. So if we take the maximum a posteriori approach, we add the log likelihood with the prior to give us a kind of an objective, which is more Bayesian motivated. So it's also possible to take an expectation of this with respect to the data generated distribution. So you could think of it as a frequentist Bayesian object. And then the problem is, how do we find the parameters? That's the math problem of this objective. If we apply the implicit function theorem, then we end up with the change in the optimal parameters will take this form. So the first term, you might recognize it as the inverse Fisher information matrix. And the second term is the partial derivative with respect to the parameters theta and the hyperparameters alpha. And the residual overfit is a first order Taylor approximation of this, or it's based on that. And intuitively, what you can say is that So the inverse Fisher information matrix is often used in experimental design. So things like de-optimality would be a way of reducing down the inverse Fisher information matrix into a score for every action. So this would be just another way of reducing down the Fisher information matrix that just happens to be practically implementable. And of course, this is just an approximation. So just to give you some kind of concrete intuition for what's going on, here's a synthetic example. So if our true reward is H and it's defined as this cubic in X in the input, and if we define a continuous action space, because that always looks nicer when you plot it, with two local optima, where the first optima will be -1, and the second optima would be around 0.4. So the true function would be on the left and the randomly generated data on the right. If we apply the residual overfit, what we're essentially doing is fitting two models. So for both of them, they both have the same architecture. It's a 3-layer neural network, each with 500 Rayleigh nodes, which is it's definitely overkill for a one-dimensional input, one-dimensional output, but I hope it makes my point for me. So the F function is going to be our attempt at regularizing this model so that it fits the data as well as it can. So that would be the blue line that you see there. And the G model, we're going to run it for 1,000 epochs, which is ridiculously overfitting. And that's, as you can see, it's going through every point that it gets to train on. And we would define the difference between these in the output as the residual overfit. Now, if we just treat that as a kind of error bar, what we end up with is these two shaded regions. The blue inner shaded region is the residual overfit without any scaling. And then the green one is just the same quantity, just multiplied by 2.58 times. If it were the case that residual overfit was a standard deviation, that would be the 99% confidence interval. Just to give you a kind of a feel for what's going on here. Now, you might be wondering at this point, why not just fit to the error that we observe in the data? So we can fit our F model to the data. Why don't we just take the same data or take separate data and just try to fit a model on the error as a function of the input? And maybe doesn't that give us the same kind of thing? So here's an example of why it gives different answers. So we took the RMSE and we generated 100 data points at the input points -1, -0.5, 0, 0.5, 1. So these are very preset points along the input. And what you would really expect is for the uncertainty to shrink almost to 0 at the points where we saw data, and then the uncertainty to be high where we didn't see the data. But on the left-hand side, we see the RMSE, which is its uncertainty prediction is pretty constant across the input, whereas the residual overfit, although it's not perfect, it does capture the essence of having higher uncertainty outside the support of the observations, or outside the observed inputs. And so what's going on is that the RMSE is combining epistemic with aleatoric uncertainty. It's combining both the uncertainty around the model parameters with the inherent noise in the data. And really, if we want to be doing effective exploration, we want to really focus our exploratory points where the model is unsure or uncertain. So that in that case, we prefer the right-hand figure to the left-hand figure. And so if we kind of turn it around, overfitting could potentially be used in the fight against a cold start. And so here's a kind of two simple ideas that use residual overfit. The first would be a kind of a UCB type approach, where the predicted reward is a sum of two things. So the first is the best estimate of the average reward, that would be our F function. And then the residual overfit takes the place of the standard deviation term in UCB with some weighting parameter alpha. And obviously we'd calculate this function for every possible action in a discrete action space, and then pick the reward that maximizes this. Just pick the greedy reward that maximizes this quantity. And the other approach would be Thompson sampling, or Thompson sampling-esque, where we replace the variance with the squared residual overfit and sample our rewards in that sense. And that's suitable for if our observations are Gaussian distributed, but you could extend this to binary rewards by using moment matching. So if you just equate the mean of the beta with the F function and the variance with the squared residual overfit, there's a simple closed form expression for the hyperparameters of the beta posterior. And so that can also be used to sample in a Thompson sampling setting. So I wanted to try this idea with real data. So this is just experimental data on public data sets. So our base model is going to be a random forest classifier, just off the shelf from scikit-learn with the default parameters. And we compare several methods for exploration. So the first would be uniform random. The second would be epsilon greedy with epsilon set to 0.1. So that means 10% of the time pick a random action, and then 90% of the time pick the action that has the highest predicted reward according to the random forest. Thirdly would be lin-UCB, which is another very popular method for exploration based on linear regression with an alpha set to 1. We can also compare it against Bootstrap Thompson sampling, where we take 20 replications of the data, train the model on each replication, and then during test time, sample which of the 20 models we're going to use in each iteration to figure out which reward model we want to use, and then pick the action that maximizes that reward model, given the context. Then finally, these two versions of Rome UCB that I mentioned. So the F function would be just the base model, and then the D function would be a single decision tree, which is trained, there's no kind of pruning going on there. So it's an overfit version of a random forest. And both F and G are trained on the same data. So that violates the first motivation for the residual overfit, but you'll notice that the second motivation I gave based on the map approach does not require that we have separate data for F and G. So I've just gone with that with that version of the method. And so what I'm plotting here, in the table, what I'm showing you is the methods across 3 different data sets of increasing number of classes. So the first column is the cover type UCI data set, which has 7 classes. And we can see that Bootstrap TS performs the best out of all of those in terms of lowest regret. And then the next number of classes would be the back corrals, which in which Rome TS has the lowest regret. And finally, the movie lens data set has the most number of classes, and Rome TS is also performing best in that. So you can see a trend here. So the more classes you add, the worse Bootstrap TS is doing in particular. So you can kind of intuitively see why that might be the case. I'm taking 20 replications of the data. What I require for a large number of classes is for these sparse rewards to be luckily sampled within the same Bootstrap in order to get a good reward model. And then as you increase the number of classes, the probability of that happening goes down much lower. And so you're in this case where you need to either increase the number of Bootstrap replications you're doing, or figure out some other more nuanced tweak on Bootstrap TS. That, for example, you might require that you replace the last layer with just the Bootstrap version, and then use the first set of layers to just do some kind of feature extraction. The problem with that is that it doesn't give you the uncertainty that's inherent in those earlier layers. And so if you can plot the sort of reward curves for these settings, for example, in the back corrals, you can see, as you would expect, the uniform random, you take the bottom right, has a very constant regret there, whereas something like Rome TS or Bootstrap TS, we have that kind of increase in gradient as the model is able to figure out the best actions for the contexts.
The scales look very different here, I guess.
Yeah, I'm sorry about that. Yeah, so the scale, the uniform random is definitely not doing as well as the other methods, but it's been rescaled. Yep, thanks for that. Good to hear your voice, because I wasn't sure if I was talking into the ether still. But,
No. Maybe I can throw in another question. Like, you're obviously having to retrain these. Like, you need fast retrainable methods here as well. That you're acting, retraining every iteration. Like every arm pull is then followed by a retrain, or you retrain FNG.
Yeah, actually, we're retraining every 100 actions.
Okay. Okay.
Yeah, so it's kind of a batched banded version with you have a replay buffer. So on every retraining, we retrain on all the data seen so far, but that happens every 100 iterations.
Okay.
Any other questions so far?
Seems good.
Cool. So I also looked at a depleting version of Movie Lens, where once an action has been performed, it no longer gives a reward of 1. It's just a reward of 0. And that's a much harder case than treating Movie Lens as a standard kind of classification bandit. And it's harder because your model can figure out which are the most popular items and recommend those. In the non-depleting version, it can just recommend the most popular items and get a pretty decent reward. But that wouldn't be very realistic. Recommended the same popular stuff is not particularly satisfying for a user. And so a depleting version of that would say that the same action just goes to 0 once it's had a positive reward. And so that explains why these curves are plateauing. And what we see is that Epsilon Greedy and Bootstrap, they plateau pretty quickly because they're not able to go beyond just the popular actions. They can't explore the kind of the power law that Ralph Hebrick was talking about earlier. Whereas Roam TS and Roam UCP and even Lin UCP can actually have this feature that they keep improving even after 6,000 iterations, which would be actually 10 passes through the data set. So I just want to wrap up here a little early. The conclusions are, I introduced the residual overfit and tried to make a case for its value in approximating model uncertainty. And then I extended it for the exploration case and made a case for this embarrassingly practical to-implement method that could potentially be built in a day. And further work on theory and to study which overfitting works best. So I have the slides and some more information at this link. And I do want to thank again the invitation to talk at this workshop, and thanks to the organizers. Also thanks to my Netflix colleagues for the very thoughtful feedback and questions on this work. So thanks very much.
Thank you, James. And are there any questions? I might start with one then. It seems to me like you could use this just like it's not only a causal thing, but you couldn't not evaluate this as just a Bayesian approximation methods and like a very cheap one and compare it in terms of like you've got compare it against MCMC on a single problem and a single fit and just see how the uncertainties of the residual overfit and MCMC or variational Bayes compare in terms of computation time and accuracy.
Yeah, so in those experiments we're using the random forest, which
maybe that's not the best. That's not the
yeah.
best place to start, maybe. But if you were using neural networks or something, you could potentially benchmark it as just as a Bayesian approximation method.
Yeah, that's right. So there's some missing examples between the synthetic example I gave and the experiments. That would be around a model that's simple enough that we can, or the data is small enough that we can run MCMC and the other approximation methods and compare that. I wouldn't expect residual overfit to really get extremely close to the true ideal Bayesian posterior. The point is that it gives a rough and ready approximation that can be used within exploration in a real world setting.
Okay, so similar to Laplace and VB maybe. I would wonder if you could just by accident get F and G close to each other, which would imply low uncertainty, and maybe it's not what you want. Like maybe is that something to worry about?
Yeah, I mean, so let's say your data happens to be very close to the prior, and you have a little bit of data, then your F is also going to be close to the prior, and the G might also be close to the prior too. And so that's one way that you want to stifle exploration. So that would be a failure case. But usually in practice, we're layering a level of exploration on top of all these methods anyway. So there's a small epsilon that is working in the background, similar to your work with the organic bandits. There's some bandit that's intervening on the case, but then there's also some organic results. And so that would help to mitigate that failure case.
Okay. Are there any more questions? Imad, who presented one of the posters earlier, is working with, he's an intern. He's using quite a different approach, which of SGLD as well. Where do you think it would compare to that as an alternative method? So
yeah, so the SGLD turned out to be very competitive in the bandit showcase that I believe Twitter Cortex released a very interesting paper that compared a whole bunch of uncertainty methods. So SGLD actually came out as one of the best across a whole bunch of settings. But obviously it's dependent on doing an SGD method, and often in industry we're not in the gradient descent mode.
Fair enough. Any more questions? Well, thanks very much. It was fascinating. Definitely a very different way to attack the problem that I thought about a lot. So thanks for that. And again, I'm clapping here alone, but I think other people are clapping sort of wherever they are. Yeah, so that draws a close to the whole workshop. Thanks to all the presenters. Thanks, well, James is still here. Thanks to all the other organizers. Thanks to everybody who came. Thanks to the poster presenters and the spotlight presenters. I think it's been fun. I think we've all learned some things. There will be a recording up online. If anyone has any material that they've presented that they would like to put on the website, you should be able to share it with me, and we'll do this. And I'd like to think we'll be back maybe in person and in the not too different future. So again, thank you, and I hope you enjoyed it. And we're also very interested to hear feedback. I might say good night now and turn it all off.